In this chapter, we will be studying radical and absolute value functions. In this lesson, we will be dividing radicals with binomial denominators.
Okay, hi everybody. So in a previous lesson we were talking about dividing radicals and how you deal with that. And we introduced this idea of rationalizing, right? If you can't simplify the radical, if you have root A divided by root B, then you can make that root A over B. If you're left with something in the denominator, okay, if you're left with a radical in the denominator or a denominator in the radical, one way or the other, then typically we expect you to do a little bit more, and we expect you to rationalize. Okay? Well, things are a little bit different if the denominator becomes a little bit more complicated. In fact, this lesson really should be dividing radicals, maybe not with conjugate denominators, but with binomial denominators. Okay? That maybe is a better way to discuss this. And so now, before I get into the description here, I just want to talk about something here. In the previous lesson here, when we did rationalizing, things were a little bit different. So let's say you had, for example, we had 3 over the square root of 5. Okay? What we would do to rationalize this is we would square the denominator in essence. So I would multiply by another root 5. But you couldn't just do that to the denominator. If you're going to change a fraction here, you got to change the denominator and the numerator by doing the same thing. And so in the numerator we would have 3 root 5. And then the denominator, remember this ended up being 5 times 5 underneath that radical, and that pair of 5s, remember, becomes a single 5. Okay? And so then 3 divided by the square root of 5 really could be rewritten as 3 root 5 divided by 5. So to get rid of that radical, you squared it. Now things are a little bit different here. Let's say, for example, that you've got an expression that looks like this. Let's say it's 1 plus the square root of 5. Okay? Now, oftentimes the mistake that gets made here is people think that in order to get rid of that radical, which is what we want to do here, okay, we're trying to remove the radical from the denominator. And in this case, so we're trying to get rid of the radical here, convert this into a form that doesn't have a radical in it. Oftentimes the assumption is that if it's got a square root in there, all I got to do is square it to get rid of the radical. But I want you to see what happens here. Okay? If you square that radical here, sorry, that binomial, you get 1 plus root 5 multiplied by 1 plus root 5. Now, this is a binomial multiplied by a binomial, so I would have to distribute the terms. I would have to distribute both terms in this first binomial to both terms in that second binomial. So 1 times 1 is 1, and then you're going to get 1 times root 5. Root 5 times 1 is going to be root 5. And then root 5 multiplied by root 5, we've already seen, is going to be 5. Okay? These two middle terms come from the distribution. 1 by 1 and root 5 by 1 and root 5. And so this becomes, well, 1 plus 5 is 6. And then there are 2 root 5 terms. So now notice that squaring the binomial does not get rid of the radical. It doesn't. In fact, it'll only get rid of the radical if you do it wrong. But that is a possibility. A lot of times people look at this, and we talked about this in the last lesson here. A lot of times people will look at this and think that that square simply distributes to both of those terms. So it becomes 1 squared plus root 5 squared, but that is incorrect. Okay, that's incorrect logic here. Now, so you've seen here that if you've got a binomial with a radical in it, squaring won't get rid of the radical. Now let's take a look at another example here. Let's say, for example, this is root 3 plus root 5. Okay, now we've got 2 radicals here. Maybe it'll be the case that square will get rid of the radicals in this case. So that's going to be root 3 plus root 5 multiplied by root 3 plus root 5. That is exactly what squaring means. We multiply it by itself. And now I'm going to distribute. Root 3 multiplied by root 3 is going to be 3. I'm going to just skip that intermediate step here. It's going to be 3. Root 3 times root 5 is going to be, well, root 3 times 5, or root 15. Root 5 times root 3 is going to be root 15. And as we've seen before, root 5 times root 5 is going to be 5. All right, well, 3 and 5, those are like terms. I can add those together to get 8. Root 15 plus root 15 is 2 root 15. Notice once again that squaring does not ultimately get rid of the radical. It doesn't. Okay? And if I was to square this again, it would be just like this first term up here or this first example here with the 1 root. Still wouldn't get rid of the radical there. Okay? Squaring does not get rid of the radical. Now, if it was this though, if it was the square root of, let's say, x plus 5. Well, this one's different because this is not a binomial. If you ignore the square root, I mean, okay, trust me, I'm not blind to the fact that is a binomial. But once you put the radical over top there, remember that bar puts brackets around the radicand there. This is one term. So if you square that, that does become x plus 5. In this particular case, the square does get rid of the radical. But in no other cases here, if you have a binomial and you square it, you will not be able to get rid of that radical in there. So then we need another approach. And the other approach is basically this right here. If you've got a plus b, if you multiply this by a minus b, I want you to see what goes on here. Now, you've seen this before because when we talk about factoring, when we introduce factoring, we talk about difference of squares factoring. So you have seen this before. We call these binomial conjugates. Okay? Binomial conjugates. And when you expand that out, a times a is a squared, a times negative b is negative ab, b times a is going to be positive ab, and then b times negative b is going to be negative b squared. And we see that these middle terms here, exact same term except opposite signs, so essentially we're going to get a squared minus b squared. So when you multiply an expression by its conjugate, when you multiply a binomial by its conjugate, you're going to be left with that first term squared minus the second term squared. And that's it. Those other terms, they canceled each other out here. Now what's beautiful about this is if you've got a radical in there, if you've got a square root somewhere in there, because you're now just squaring the individual terms, now that square will get rid of that radical. Okay? But this is the only way to do it with this binomial conjugate. Okay, and that's really what this lesson is about here. Okay, we talk about, first of all, what the conjugate binomial is. And so if you've got x plus 6, its conjugate is x minus 6. Let's say you've got root x minus 3, its conjugate would be root x plus 3. Okay, these right here are not conjugates because technically they're not binomials. Okay? This is a monomial, this is a monomial. Now, if you were to multiply them together, you would utilize the rule for multiplying conjugates. Yes, you would, because the binomials inside them are conjugates, but the whole term together, they aren't because they're considered monomials. So, what we're going to do, when you've got a binomial in the denominator that has a radical with it, what you're going to do is we're going to multiply numerator and denominator by the conjugate of the denominator, okay, blah, blah, blah. We're going to multiply that out, and that should deal with our problem. These two steps here just talk about how we do that. But I've already kind of gone through and shown you an example. So really what we're going to do now is we're just going to jump ahead here and just do a bunch of examples so you can see it done over and over again. Right, so the question is asking us to simplify and rationalize the denominators of each of the following. All right, so here we go. So we've got a root 2 minus a 7 in the denominator. It's a binomial in the denominator. So I'm going to multiply numerator and denominator by the binomial conjugate. Because we've just seen that if you try to square that denominator, squaring does not get rid of a radical if you're squaring a binomial. Now up in the numerator, you might write it as just 4 times root 2 plus 7. Okay. In the denominator though, bear in mind what's going to happen here. Root 2 times root 2 is going to be 2. Root 2 times positive 7 is 7 root 2. Negative 7 times root 2 is negative 7 root 2. And then negative 7 times 7 is going to be negative 49. Okay. Now, up in the numerator, I might still leave that as 4 times root 2 plus 7. I might not multiply that out quite yet. And I'll explain why in just a moment here. I know that my 7 root 2's are going to cancel. And in fact, this is probably going to be the last time I'm going to write that out here. Simply because my choice of using the conjugate is done on purpose. It's a very purposeful choice because I know that those middle terms will disappear. And that's why I did that. So maybe I'm not going to write those anymore. Now I'm left with 2 minus 49. That's going to be negative 47. Okay, so that's my answer here. Now at this point here, I'm just going to kind of clean it up a little bit. Now maybe at this point, I might think about multiplying the 4 through that binomial. Now the reason why I waited up until this point here is because if 4 has got a common factor with that denominator, maybe I would have canceled something in there first before I multiplied it through, but it doesn't. I'm going to move that negative in front of the whole expression because it looks better in front of the whole expression, or up in the numerator. Negative always looks a little awkward down in the denominator. It's not incorrect, it just looks a little weird. Then you multiply that through 4 root 2 plus 28. So I make sure that the negative is in front of the whole thing, so that indicates that it would be distributed to both terms in the numerator. Okay, and there we go. So let's do it again. So 3 root 5 multiplied by root 6 plus 4. Okay, now I see a composite number there. 5 is prime, so I can't simplify that, but I do see that 6 is composite. However, I know that the only factors it has got in there are 2 and 3, and so I'm not going to be able to simplify that down anymore. So I will multiply the numerator and the denominator by the conjugate. Okay? So in my numerator, I'll leave that as 3 root 5 multiplied by root 6 minus 4. I'm going to leave that just for the time being, because I don't quite know what I'm going to get here in a second. And if I can simplify something first, it's easier if it's factored first. In the denominator, because I chose to multiply by the binomial conjugate, I know that the middle terms are going to cancel. So it's going to be root 6 times root 6, 6. And then I'm going to skip the middle two terms here. 4 times negative 4 is going to be negative, whoops, sorry, not negative 10. That's embarrassing. I'm anticipating where this is going. Negative 16. Okay, so that's going to be 3 root 5 multiplied by root 6 minus 4 all over, well, 6 minus 16 is going to be negative 10. All right, well, ideally I'd like to cancel something there, but I can't. Okay, 10 and 3 don't have anything in common. I can't cancel the 2 that's common to the 10 and the 4, not unless I decide I'm going to distribute the 10 to both those terms and basically split them up into 2 different terms. And before I do that, I really should distribute out that 3 root 5 so that I make it very clear that there are 2 terms in the numerator. 3 root 5 times root 6 is going to be 3 root 30. Okay, remember the coefficient here is 1, so 3 times 1 is 3. Root 5 times root 6, you would multiply the radicands. And then 3 root 5 times negative 4 will be negative 12 root 5 all over negative 10. Now, granted, this term and this term share something in common, but this term and the denominator and the first term don't. So maybe I would just leave it like that. Okay, there's really no need to distribute that 10 to both. The one thing I might do at this point, though, because I don't really like the way the negative looks in the denominator, is I might move it in front of the whole expression. Okay? Or I might move it up and put brackets around the whole numerator, just to illustrate that that negative gets distributed through. Okay, but it means the same thing if it's written in front of the bar there. Let's do some more. Oops, sorry. Here we go. Here's an interesting one because we've got a binomial in the numerator as well. Okay, now before I get to rationalizing here, first thing I want to notice here is, oh, look at that, root 8. I know I can simplify root 8 because that's been a question that has been simplified repeatedly. Okay, so we know that 8 is 2 times 2 times 2. There's a pair of 2, so I can make this 2 root 2 minus root 3 over 4 root 3 minus root 2. I'll just make that one itty bitty little change there. Okay. Now, I've got a binomial in the denominator. I am going to multiply by its conjugate. So I'm going to multiply by 4 root 3 plus root 2. And I will multiply that through in the numerator as well. So this question is going to require a little bit of effort on my part because I've got 2 binomials multiplied together. In the denominator, they're conjugates, so it's going to simplify a little bit here. And I already know how that's going to work here, but the numerator really isn't. I'm going to get 2 root 2 times 4 root 3. So 2 times 4 will be 8. Root 2 times root 3 is root 6. 2 root 2 will then multiply by root 2. Okay, well, wait a minute. I'm going to end up multiplying a root 2 by a root 2. Those are going to cancel to give me a 2. And then there was this other 2 right here that I got. So this is going to end up being positive 2 root 2 times 2. And now just for kind of expediency's sake, because I'm going to run out of room here, I know that that's going to be the same as pulling out a 2. And so then that 2 that I had initially times that 2, that's going to give me a 4. It's kind of nice. I get a similar sort of thing when I multiply this negative root 3 by 4 root 3. Well, root 3 times root 3 is just going to give you a 3, multiplied by that 4 that was left over there. So it's going to be negative 12 when I multiply that through. And then finally, negative root 3 times that positive root 2. I multiply the radicands together. So the coefficients will give me a negative, and this will be root 6. All right. Down in the denominator, I already know that the middle terms are going to cancel each other out. So I'm not even going to bother with those. So I'm just going to square the first term and square the second term here. But I got to be careful here. When people do this, 4 root 3 multiplied by 4 root 3, see, it's very easy to remember that the radical, root 3 times root 3, is going to be positive 3. That's easy because we're in a chapter right now, we're talking about radicals, we mention that a lot. It's very easy to forget that the 4 in front also gets squared. So this becomes 4 squared times root 3 squared. Well, 4 squared is 16, root 3 squared is 3. And then you're left with 16 multiplied by 3, it's going to get you 48. Now, if you want, you can go to your calculator and do that. Just make sure that when you write it in your calculator, it's 4 root 3. Put brackets around the whole thing and make sure you square it like that. You will get 48. And then I'm going to get negative root 2 times positive root 2. That's going to be a negative, and then root 2 times root 2 is 2. Okay. Now, in the numerator, I got to group together like terms. I've got 8 root 6's here, and I'm subtracting a root 6. It's going to give me 7 root 6. Well, this isn't looking so good for simplifying because 7 is a prime number. 4 minus 12 will get me negative 8. And in the denominator, 48 minus 2 is going to be 46. Now, if I was to simplify this, now you'll notice here 7 and 46 don't have anything common. I don't even worry about the root 6 because the root 6 and this integer here, they're completely different types of numbers here. They're not common. But 46 and 8 have something in common. But unless I'm willing to split that up and make this 7 root 6 over 46 minus 8 over 46, split that up into 2 terms, I can't simplify anything. So that would be the end of that question. All right? Okay, wow. Okay, this one here, notice that basically the numerator and denominator are conjugates of each other. But it turns out when I'm simplifying this, I don't really care what the numerator is. It really makes no difference. It doesn't matter that it's the conjugate of the denominator. I have to multiply by the conjugate of the denominator to rationalize this. So up in the numerator, I end up squaring that binomial. In the denominator, I'm just multiplying by conjugates. So in the numerator, I got to pay careful attention to this because remember, when you square a binomial, which is what I'm doing there essentially, okay, it's root 3x plus 4 root 3 multiplied by itself. This is not going to get rid of my radicals. Now root 3x times root 3x will get rid of the radical there. That'll be just 3x. But root 3x times 4 root 3 is going to be 4 root 3 times 3x. Now I'm going to write it like that because you can see right away there's going to be some simplifying. Here I'm going to end up with the same thing, 4 root 3 times 3x. And then at the back here, and we've already done this before where we had 4 root 3 and we squared it. We already know 4 times 4 is 16. Root 3 times root 3 is 3. Multiplied together, it's going to give me 48. I'm going to come back to that in a second here. Now let's look at the denominator. I already know that because of there's our binomial conjugates, I already know that it's going to be the first term squared, which will give me 3x. And then the final term squared, but negative, okay, because the negative times the positive will be negative 48. Okay, well, there's a common 3 down there in the denominator. That might end up being something important here. We'll see about what that looks like in just a second here. Up in my numerator, these are going to simplify down. Okay, I'm going to pull out the 3 in both cases, so it's going to be 12 root x. And it turns out there's going to be 2 of them. So 12 root x, or I should say 12 root x, there's going to be 2 of them, so it'll end up being 24 root x plus 48 all over 3x minus 48. All right, that's looking really good. Now notice in the numerator once again that squaring that binomial did not get rid of the radical. We were stuck with the radical, okay? But look what I can do. There is a common factor of 3 to all 3 terms in the numerator. I can factor that out, and I'm going to be left with x plus 8 root x plus 16. There's also a common factor of 3 in the denominator, 3 multiplied by x minus 16. Now, I can cancel factors. Okay? I can cancel factors. 3 divided by 3 works in this case. And so this is going to give me x plus 8 root x. Oh, I don't want to go off the screen, and I am going off the screen, so here we go. Plus 16 all over x minus 16. Okay, and that's what that would look like, as simple as we can make it. All right, let's look at a couple more, just a couple more. So here, again, I see a binomial in the denominator, so I'm going to multiply by the conjugate, so 4 plus 5 root 5, 4 plus 5 root 5. I'm going to worry about the numerator first, because that typically is going to require more work. There is, by the way, nothing to simplify here, because the radicands here are all prime numbers, so they're as simple as they're going to get. Root 5 times 4 will be 4 root 5. Root 5 times 5 root 5. Okay, I'm going to write that out like this, just so that you see it here, and I'll simplify that in a second. But that's 5 root 5 times root 5, so that there's 2 5s in the radicand. 2 root 2 times 4 is going to be 8 root 2. And then 2 root 2 times 5 root 5 is going to be 10 root 10. Now I take the liberty here of multiplying those out here because 10 has only got one of both those factors showing up here. There's only 1 2 in there, there's only 1 5 in there. There's nothing to simplify. In your denominator, we're going to ignore looking at the middle terms right now. I'm going to get 4 times 4 will be 16 minus, okay, 5 root 5 squared. Now I haven't done that yet. I had it simplified up there here. But that's going to end up, or sorry, I didn't have that exactly up there, but 5 root 5 times 5 root 5, well 5 times 5 is 25. Root 5 times root 5 is 5. And 25 times 5 is 125. Now, simplifying the numerator, that pair of 5s becomes a 5 here. So this will become 5 root 5 plus, that's 25. This root 5 times 5 becomes a 5 that I multiply by that 5, so 25. Minus 8 root 2, that's about as good as that's going to get, plus 10 root 10. Now notice, there are no common terms there. There's nothing else I can do to put those all together. In fact, there's not even a common factor all the way through. Before you say 2, 2 is a factor of 4, 8, and 10, but it's not a factor of 25. So that doesn't work here. And then when I take 125 away from 16, I'm going to get negative 109. Okay? So now, the only thing that I can really do here is bring that negative and write it out front. So this will be negative 4 root 5 plus 25 minus 8 root 2 plus 10 root 10 all over 109. Okay? That whole term is negative. I might even put parentheses around the whole thing just to make sure that that negative is out front. All right, one last term here. Root 2 minus root 6 plus root 2 plus root 6. So we're going to multiply by the binomial conjugate of the denominator. There is a little bit of factoring that you can do here. Now, because we've done a bunch of examples of this, I want to show you really quickly just that little bit of factoring with this question that we could do here. Okay? So this would be the same as root 2 minus, now 6 is the same as 2 times 3, so this really could be broken down into root 2 times root 3. Down here, this is root 2 plus root 2 times root 3. So the reason I do it like this is because there is a common root 2 to all of those terms there. I can take a root 2 out of the denominator and it would be 1 minus root 3. I can take a 1 out of the denominator, which would give me root 2 times 1 plus root 3. And then root 2 divided by root 2 is just 1. And so this actually simplifies down, this question simplifies down to this. 1 minus root 3 times, divided by, I should say, 1 plus root 3. And now I'll multiply by the conjugate of the denominator. And it's just a little bit easier for me to do it when it's written in this form. Okay, the numerator is going to be 1 minus root 3 minus root 3, and then I'm going to get negative root 3 times negative root 3 will become positive 3. The denominator, because they're conjugates, I don't need to worry about the middle terms. 1 times 1 is 1. Root 3 times negative root 3 will be negative 3. Now, 1 plus 3 is 4, and then I've got negative 2 root 3 there. And then 1 minus 3 is negative 2. Now, I am so close here, and I'm going to show you just a slightly different approach because I want to address where a lot of people make little errors here, and I want to show you the correct way to approach this. A lot of times people see like 4, they'll divide that by the negative 2, they'll forget to divide both terms by it. Now, one thing that you could do is to factor out the common 2, and that's what I did in a previous question, and maybe I'll do that over here, just so you see both here. But another thing that I could do here is distribute that negative 2 in the denominator to both those terms. So 4 divided by negative 2, minus 2 root 3 over negative 2. 4 divided by negative 2 is negative 2, and then the negatives 2 cancel, so do the negatives there, so this will become positive 3. So negative 2 plus root 3. Or I could take out, for example, I could divide both of these terms by a negative 2, which will give me negative 2 plus root 3 over negative 2, which is what we did in a previous question, and then the negative 2's cancel, so you're left with negative 2 plus root 3. Either way, you simplify down to the same thing. It's just that if you ever get into a position where you're looking at this and you're thinking, well, I can cancel that out here, bear in mind that as soon as you do that, you're essentially distributing the denominator to both terms. Please make sure you actually do distribute the denominator to both terms if you're trying to cancel like that.